Hi everyone, and welcome to the last chapter in Organic Chemistry 2, the amines chapter. Almost saving the best for last, right? Our nitrogens are going to be the star of the show this chapter, and this will cover slides 1 through 9. The amines, I thought it's kind of cool to show you a graphic of how prevalent amines are in very bioactive compounds. You can see in morphine, there is a nitrogen on the left that is in an amine functionality. Cocaine has an amine functionality, which is a stimulant. Nicotine is basically the only functionality apart from the aromatic ring is the two amines. Adrenaline has a very important amine at the end, and you can see how adrenaline, which is our fight or flight hormone, noradrenaline, which regulates heart rate and dilates air passages, and dopamine are all related to one another. They're very derivative of each other. I've always found it interesting that you can start to see trends in function based on skeletal formations, and nothing shows this better than the morphine rule. So if any of you guys are not familiar with the morphine rule, you can see that if a molecule contains a benzene ring, I'm going to make this a little smaller. If you have a benzene ring and it's connected to a quaternary carbon, that means a carbon with 4 carbons off of it, right? 1, 2, 3, 4, no hydrogens effectively. And then you need 2 carbons spacing, so 1, 2. And then that second carbon needs to be attached to an amine, and it needs to be a tertiary amine. Again, that nitrogen cannot have any hydrogens on it. And if you follow that, you can see that this is exactly what morphine has. The benzene to a quaternary carbon, 2 carbon spacer to a tertiary amine. Every single one of these molecules follows the morphine rule. And what that means is that it binds to the same portion of the brain and delivers its effects. So you can see that at the top row, you can find the natural opiates, morphine, codeine, opravin, and theobromine. And then down below, you'll see some semi-synthetic opiates. Maybe the ones that you've heard of are things like Vicodin, Percocet or Oxycontin, Narcan, heroin, right? And Dolofen, which is also methadone. Now, of these, you can see that methadone, which is typically used to treat addictions, has that benzene ring to a quaternary carbon, to a 2 carbon spacer, to a tertiary amine. So it follows the morphine rule, so it will bind in the same pocket, but it's very different. So it delivers the effects that the opioids, what an opioid does, the methadone doesn't deliver the same type of effect. However, it does bind to the same area. So you can start seeing trends when you're classifying compounds. We've seen trends for steroids, the 6665 system. And this is where you guys can get a little savvy when you open up your medicine cabinet and look at the structure of the compound you might be taking. You may be seeing some of these trends as you consider what the pharmaceutical does. Now, amines are in a class of their own as a functional group because they are basic. They are not very electronegative, right? Nitrogen, they're electronegative-ish, but they're not super electronegative, not like a halogen or even an oxygen. And given that it does have a lone pair in its normal formal charge 0 state, it's very generous with it. Thus, it serves as a pretty decent base. Overall, we see that the nitrogen, and I can highlight that here, the nitrogen here is technically in a tetrahedral format, but one of those areas is taken up by a lone pair. Thus, the geometry that we attribute it as having is in fact pyramidal or trigonal pyramidal, because we only look at the 3 bonds. We sort of exclude the lone pair when we actually give it its final geometry. It would appear, given that it technically has a tetrahedral shape, that amines would have the ability to be chiral, since if you count the lone pair as its own group, as unique, then it technically could have 4 different groups off of it. However, despite that, we never really see the nitrogen being a chiral atom or a stereocenter. And the reason for this is because the nitrogen, which is located right here, because that 4th area is a lone pair and not a bond, this orbital, which exists as both above and below the nitrogen plane-wise, has tunneling effects, right? So we see rapid isomerization or inversion of the nitrogen. So let's just say that, let's make this an ethyl. Let's make this a methyl. So what I did is I actually changed this group. Therefore, there are technically 4 different groups on the nitrogen. If I were to prioritize them and give it a designation, R or S, I would say that the lowest priority group is in the back. We'll call it hydrogen. We'll say it goes, highest priority is the ethyl, followed by the methyl, followed by the lone pair. Let's just, as long as we keep it consistent, we'll be okay. So if the hydrogen's in the back, we go 1 to 2 to 3, that is R. Okay? However, because the electrons can tunnel, right, through the little orbital on the other side, basically the electrons could be here and they can tunnel through and be on the other side, back and forth, back and forth. This tunneling isomerizes the nitrogen. So in the midst, what happens is that lone pair is somewhere in the middle. It kind of goes through an sp2 hybridization on its way, right? So now it's sp2 on its way to being fully isomerized in the other direction. So now it goes back to being sp3. If I now look at the prioritization, again, keeping everything the same, hydrogen's in the back and it's still number 4, ethyl is number 1, methyl is number 2, and I arbitrarily put the lone pair as number 3. Technically, this would be 1 to 2 to 3. This is S. So because it's going back and forth, back and forth, back and forth, tunneling with those electrons, we don't see nitrogen as ever being a stereocenter in this case. A little bit more on physical properties. Well, nitrogen is analogous to oxygen in that amines have high boiling points due to their ability to hydrogen bond, right? Again, the nitrogen, if it has hydrogens on it, has a dipole, or at least it has an electronegative bond. There is a difference between having, right, the nitrogen is partially negative, therefore the hydrogen is partially positive. That's a polar bond, and it's attracted to other NH bonds, maybe in a different molecule or the same molecule of itself. So hydrogen bonding is something that can happen for amines. Therefore, high boiling points and high melting points often result in molecules with hydrogen bonding for amines. However, boiling points are lower than alcohols because NH bonding is weaker than OH bonding. Why is that? Well, again, oxygen is more electronegative. And therefore more tightly holds those electrons. That pull is tighter towards that oxygen, that greedy oxygen. nitrogen being not as electronegative and a little bit more generous. So the spacing, the bond length is a little different and less potent. There's also, if you were to say which bond is more polarized, you could say, well, the oxygen's more electronegative, therefore it makes the hydrogen more electropositive. And if I were to reflect that in the size of my partial charges, you still see a polar bond, but a less severe polar bond. We can classify amines just like we can classify other functional groups relative to being primary, secondary, or tertiary. And this is more like carbons. Okay, so this is going to be more like carbons. If you have NH3, it's just ammonia. If you put one carbon group, like a methyl or an ethyl or a propyl, off of the nitrogen and the other two are still hydrogens, this is a primary amine. When you have two carbon groups off of the nitrogen, it's called a secondary amine, and 3 carbon groups off of the nitrogen, hence no hydrogens, is a tertiary amine. We saw this classification up here for the morphine rule, right? Tertiary amine, the nitrogen cannot have a hydrogen on it. It has to be substituted by 3 carbons. Some other really fun examples of amines in useful compounds that you may or may not use are things that have good stories, at least, are serendipitous discoveries, right? And we all love like the classic stories of how people find out a great discovery by complete mistake. And this happens quite a lot in the pharmaceutical industry. And this is when you're paying strict attention to side effects, right? Sometimes the side effects are not what you are going for, but end up being better than maybe what you designed the compound for. And so some examples are as follow. Zyban, right, or bupropion, was developed as an antidepressant, but it was found to help patients quit smoking. So this was found out during clinical trials when you're paying strict attention. So they kind of scrapped it as an antidepressant, but now it's marketed under the trade name Zyban, and it's a smoking cessation drug. One of my favorites, makes me laugh, is Viagra. Viagra, true story, was named because in jest, the employees at Pfizer were joking about how it should be a combination of Niagara Falls and vigor. And that's where the trade name Viagra comes from. But sildenafil, which was designed to treat angina, right, chest pain that occurs when heart muscle receives insufficient oxygen, that's what the original molecule was designed to treat. But in clinical studies, they found the surprising erectile functions being treated. And so when those side effects were being reported, it was found that it wasn't such a great angina drug, but it worked great for erectile dysfunction. So now you can see how annual sales bolstering above $1 billion for some effective side effect that was unexpected. This one baffles me. I'm always super impressed by how Johns Hopkins figured this one out. So you guys are probably very aware of Benadryl, diphenylhydramine. You can read it on the back of your Benadryl bottle. This molecule is a first-generation antihistamine, but it is very sedating, right? It's how we always joke about put your kids to sleep on a plane, just give them some Benadryl, because it's highly sedating. While 8-chlorotheophylline, which is shown on the right, if you recognize caffeine, you'll see that this is very similar to the caffeine molecule. It's a derivative of caffeine, and it has the same type of function as caffeine. It's a stimulant. So it was thought that if you mixed these two, you might reduce the sedation imposed by diphenylhydramine but keep it as an antihistamine, but not, kind of make it the daytime version. Unfortunately, the sedating effects were still too strong and overpowered the effects of the stimulant. But when the mixture was clinically tested, and this was in 1947 at Johns Hopkins, One patient suffering from car sickness reported that their symptoms were better. Further studies confirmed that this mixture is actually effective against motion sickness, and this combo was the mother of Dramamine. I mean, this is how Dramamine was invented. And now it's been replaced by non-drowsy formulas marketed as Dramamine 2. But again, that is some very, very aware people who can report, oh, it's not helping my allergies, but boy, I'm not car sick anymore. I mean, to pay attention to those seemingly unimportant side effects is pretty amazing, because that's a drug still on the market today. So the next few slides, we'll be talking more about the amines chemical properties. And as I mentioned, nitrogen is not as not as electronegative as some of the other atoms like oxygen and halogens. Therefore, since it has a lone pair, it's more generous with that lone pair. So what we're going to see in this chapter is that amines can function in two ways. They can function as a nucleophile, which also is a base, right? A good nucleophile is a good base. They are the same species. We just define them differently based on how they behave. So for instance, here's a nitrogen reacting with HCl, an acid, and the nitrogen's attacking the HCl and protonating itself and forming an ammonium species. The pKa of an ammonium ion is 10. Okay, and the ammonium ion is actually what predominates in physiological pH. We know that because we've seen this whenever people write an amino acid. They always write it as a Zwitter ion, meaning the nitrogen of the amine is always protonated. Why? Because the ammonium ion predominates at physiological pH. Ammonium ions are stronger than water or alcohols as an acid, but weaker than carboxylic acids. So therefore, the equilibrium lies towards the weaker acid. That's why the carboxylate is deprotonated and the ammonium prevails. We'll also see nitrogen behaving like a nucleophile. So notice I could start with the same system as I did above, but instead of reacting it with HCl, I'm going to just do an SN2. The nitrogen can perform this nucleophilic behavior, kicking out the good leaving group and giving us another ammonium species. Notice that an amine does not need to be formally negative to serve as a base, or a nucleophile for that matter. Why? Well, we've already mentioned it, right? Nitrogen is not strongly electronegative. That means it's not super greedy, right? Not greedy. So it's willing to use its electrons and go out and attack something. The second way we're going to see amines behave is as a leaving group. Guys, we've already seen alcohols become good leaving groups and do SN1 chemistry, right? We've seen even OH leave in some of the chapters we've just looked at, like in the elimination of the aldol condensation. So nitrogens have that function as well. And so we're going to see how to do that in this chapter. Acid-base chemistry of amines, a little bit more. Amines serve as moderate to mild bases. So we're going to see amines be bases in this chapter. I also wanted to note the sense that although it is a base, it is a mild base. It's a moderate to mild base. It's not super strong. We often use amines to quench, or ammonium systems, which are weak acids, to quench in our workups. And here I just want to show you that the acidity of an amine, not an ammonium, is weak. So an ammonium, as we mentioned in the previous slide, the ammonium ion is about 10. So let's carry that over here. So the pKa of an ammonium ion is about 10. So it's a good acid. Remember, water is 15.7, and a carboxylic acid is about 4 to 5. So I just want to give you that range. So ammonium is better than water, but not as good as a carboxylic acid. What if the nitrogen, though, what if I have an amine where one of the groups off of it, I don't have an ammonium species. I have a system down here, an amine where I have a proton on it. How difficult is it to take that proton off and get to a negative nitrogen? Right? So how acidic is it if it's not in the ammonium form where it's out of its bond trend? What if it's in its bond trend and you want to pluck off a proton? Well, it's not as easy to do. The pKa of an amine in its normal bond trend is about 35. Let's rationalize that. If I had a base and I removed that proton, you would see the negative nitrogen and the acid. Now, let me remind you that last chapter we used diisopropyl amide, lithium diisopropyl amide, or LDA. This is a strong, bulky base. So you know about nitrogen minuses. They're very strong bases. And let's make sense of this. An amine with a hydrogen on it, the pKa is 35. It is not a good acid. It's not like the ammonium species. So an amine in its normal bond trend with a proton is very difficult to deprotonate and form the negative charge. But what does it say as a base? If it's not a good acid, its conjugate is a strong base. So I just wanted to use our acid-base equilibrium, work out what we know, what we've used to sort of make sense of this. Don't be confused between deprotonating an amine in its normal bond trend and the pKa of 10 when an ammonium species is outside its bond trend and wants to give up a proton. Those are two very different pKa's. The last slide in this section, again, reminds you about LDA. Examples of strong amine bases that we have already used. These are tough to make. You actually have to use another really strong base to make the extremely strong base. And LDA is actually made fresh right before you use it. If you go on sites and request information like, should I buy LDA or should I make it? 99% of chemists will say, just make it fresh when you need it. You can buy diisopropyl amine. You know, it's a very stable liquid amine. And then you have to use very unstable N-butyllithium is a very strong base, and this is strong enough to deprotonate and give us the negatively charged nitrogen. We usually make LDA right before we use it. It has to be done at negative 78 degrees. It's highly reactive, and we don't want to expose it to air because even the protons and the moisture of air will react with LDA. A little bit about the basicity of amines and how other aspects of what's around the functional group can affect it. And we've already done a problem like this in another slide in a previous chapter. If I were to give you these two compounds and ask you which one is more basic and why, have a think about it. Well, think about the ability of that nitrogen to attack, I don't know, a proton. A way to look at it is to say, an amine's basicity is based on its lone pair. How easy is it for that nitrogen to use its lone pair and go and make a new bond with something, right? Because a lone pair is yours and yours alone, but a bond is a sharing. right? A covalent bond is sharing. So who has a lone pair all to itself? Is it 1 or is it 2? Who owns its lone pair without the bother of sharing with anybody? Well, if you said 1, then you'd be correct. Understand that the nitrogen on 2, those lone pairs are not really localized on the nitrogen. We could draw an array of multiple resonance structures for this guy. That lone pair is in resonance around the whole aromatic ring. It's donating into the ring, lots of resonance going on. That lone pair is shared among many atoms. The lone pair on the left, though, is isolated and localized on that nitrogen and is free to be used whenever that nitrogen deems fit. So this molecule, the amine with the cyclohexyl ring off of it, is the more basic molecule. Not to say that the other one cannot be a base. It can, it's just weaker. Another thing of note is the effect of hybridization on basicity. You can liken this to the trend we saw in ARIO. Remember in ARIO, for orbitals, we saw that a hydrogen on an alkane, the pKa was like 50. The hydrogen on a vinyl carbon, because the vinyl carbon would have a negative charge or a lone pair in an sp2 orbital, is about, I don't know, 40, 35, somewhere in that vicinity. And then once you put the hydrogen on an sp carbon, it drops to 25. And so ARIO tells us that when a lone pair sits in an orbital that has more s character, it's lower in energy and more willing to give up the proton. So the more s character, the better the acid, right? More s character equals better acid. That's what we see. Therefore, it's the reverse, right? If you think about basicity, the less s character, the better the base, because then it's less stable and more willing to react. So if you have an amine where the lone pair is on an sp3 hybridized nitrogen, it's better than an amine that is part of a vinyl system on an sp2 system. Or if you have an amine where the nitrogen's lone pair is on a nitrogen that's sp. So it's the same trend, but in reverse, but for obvious reasons, right? The more S character, the more the negative charge resulting for acids is better. But the lone pair sitting on a nitrogen in those same environments, we don't want it to be stable, we want it to react. So therefore, we see the reverse trend. Electronegativity thus varies with hybridization, and so this also works towards this trend as well.